Welcome to Horizon's Technical Talks, where we stay up to date on a lot of the current results in quantum computing. Today we have Ben Brown, who's a postdoc over at the University of Sydney, who works on different implementations of fault-tolerant quantum computation using topological codes. He's going to talk for a little bit about doing quantum error correction with a mix of continuous and discrete variable codes. Questions and answers should be in the little Q&A on Zoom, and we'll get to them at the end. Without further ado, take it away, Ben.
Hi. Thanks for having me to talk. It's nice to be talking in the middle of the day. I'm used to having to either wake up very early to talk to the US or stay up very late to talk in Europe or one way or the other. So it's nice being on almost the same time zone as Singapore. I'm going to tell you about my work with a bunch of people on practical quantum error correction with the XZZX code and Kerr-cat qubits. And to summarize, the message is we're excited about it because it has very good thresholds, and right now one of the hardest things seems to be getting qubits that are below threshold error rates, and we think this is a very promising proposal. Okay, so this is it's kind of built out of quite a lot of work with a few people. So I'm mostly going to talk about this paper that we just put on the archive last month, that's there in the middle, that I wrote with David Tuckett, Andrew Damoan, Anna Grimsmo, and Shruti Puri, which is the practical implementation where we realize a code with Kerr-cat qubits. But to get to here, we did a lot of work with, well, first of all, not so long ago, we had a paper published on what we called the XZZX code with the people at the bottom of the page there, Pablo, David, and the Steves. And to make all these decoders, we had to do some kind of wacky things, me and Don Williamson, who you can see at the top left there. So I'm going to go maybe around the houses to the practical result, and I'm going to talk a bit about the theory of quantum error correction along the way. I just finished making the slides earlier today, so I don't know how long they're going to take. It might be an hour, it might be less. So ask me some questions. This is it's a really great collaboration, I think, because I don't think any of the co-authors in this most recent paper certainly could have done the whole paper by themselves. Like, really, I would suggest after having me explain the codes, you should also go see a talk by Shruti or Anna, who can explain the qubits much better than me. So I'm going to do my best to muddle through those parts, and I might have to defer a few questions to them if you really push me. Okay, so let's start by just talking about the repetition code, because this is going to explain a lot of why the XZZX code is really good at doing what it does. So this is classical error correction, and the easiest code is just a one-dimensional string of bits, and the bits can take values +1 or -1, and we encode a logical bit by just asking all the physical bits to agree. So we might say if all the bits are in the +1 state, so I've got kind of a physics idea in mind where spins are +1 or -1, they're bits. So if all the bits are in the +1 state, it encodes a 0, and if all the bits are in the -1 state, then it encodes a 1. That's the classical code, and it has a very high threshold, as I'll explain shortly. So we want to check for errors with this code. And for that, we have parity checks. And as I said, if there are no errors, all of the bits are supposed to agree. So the best way to check for an error is to ask if a bit agrees with its neighbor. So we can check, for example, sigma on two nearest neighbor spins. And if they agree, then we don't think any error has occurred. And if they don't agree, then we should suspect that an error has occurred. One of the bits is flipped to the wrong state, and we have to figure that out. And that's what's called the decoding problem. We need to decode all kinds of codes, and this is an easy one to start with. So how do we decode the repetition code? So here I've drawn it at the top where I've added some errors. The errors are the red bits, and the black ones are the state I encoded in the first place. And you can see where the neighbors don't agree by these big yellow diamond shapes. So I'll call those defects. The defect is, a signal where a parity check is lit up saying an error has occurred here. And the parity checks have lit up because this bit doesn't agree with this bit because an error occurred. And yeah, so they don't agree. However, I've actually drawn a whole string of errors here, and no defects appear in between these guys because they both, this bit agrees with this bit because they're both flipped and two wrongs haven't made a right. So really what we have is defects at the ends of strings of errors. And yeah, so as I said, we should really regard these as strings, these errors of strings. So here's a whole string of red flip bits, and they connect up these defects. There's another smaller string here. Okay, so if we assume that the error rate is small, which is what we want to do, we want to find the smallest error that could have given rise to a pattern of defects. So we call some whole pattern of defects the syndrome, and the job of a decoder is to work out what error gave rise to a syndrome. So in this case, for just the 1D repetition code, we have to compare two different kinds of strings. So we might consider the strings that run between these defects, the ones I've shown in the picture, or we might look at the alternative set of strings, where say the string might have ran through these black defects from here to here, and maybe this guy went on to somewhere else, and that could be an alternative error which could have caused it. But if we assume that the error rate is small, then we just look for the shortest set of strings that could have given rise to that pattern of defects, and then we can correct for the bits according to that. And it shouldn't be too hard to see that as long as the error rate is smaller than 1/2, then for a sufficiently long repetition code, then probably your decoder is going to get it right. And that's the repetition code. So, an important idea for decoding these kinds of models is that of conservation laws. So it's really inherent in the structure of the repetition code that these defects appear at the endpoints of strings in pairs. And actually using this insight, we can decode all kinds of other stuff. And this is what I did with Dominic Williamson, with some slightly more wacky codes, but in fact, it's pretty interesting just looking at other kinds of code. So here's a quantum error correcting code that we call the toric code, or the surface code. And so the surface code, the difference between a quantum error correcting code and a classical error correcting code is a quantum error correcting code needs to protect an entire, it needs to protect a whole qubit, which may experience both bit flip errors and dephasing errors. And a classical repetition code is only set up to deal with bit flip errors. So really what happens, the problem of decoding is very much the same for the quantum code and the classical code. The difference, though, is that while we have to increase the dimensionality of the problem to make a code that can protect against both bit flip errors and dephasing errors. However, the problem of decoding is really still finding defects that that pair up with each other, and errors still appear like strings. So this is really it should be familiar from the 1D picture we just looked at, but here is the error. So it looks like a whole string of qubits on the surface of this two-dimensional lattice of qubits that are flipped, and the stabilizers that light up, or the parity checks that light up to spot this error, they live at the endpoints of this string. So we have a decoder that we call min-weight perfect matching, and the job of this decoder is a little bit harder than the 1D repetition code, where we only had to compare, say, two possible strings on a 1D line. Now we have a whole two-dimensional plane with lots of error strings. We need an algorithm called min-weight perfect matching to deal with this. Maybe you can pick other algorithms, but this is the easiest one to imagine. So min-weight perfect matching, it looks for the locations of all the defects, and it looks for the shortest possible string that could pair up those defects. So as I said, it's actually structural. There is some structure in the model that gives rise to this, the fact that errors are strings and defects appear at their endpoints. And yeah, so what Dom and I suggested this was is what we call a symmetry, and a symmetry gives rise to a conservation law, like the Noether's theorem of quantum error correction. So the way to see that we have this conservation law is by looking at the stabilizer group. It should be inherent in the stabilizer group. So specifically, if we take all the stabilizers of the toric code and multiply them all together, we get the identity. And so I guess I have rushed a little bit in explaining some of these things, but so the stabilizers of the surface code, there are Pauli matrices, and their eigenvalues are only plus or minus 1. So if you can find some product of some bunch of elements of the stabilizer group that give identity, and you know that its eigenvalue has to be plus 1 because all the eigenvalues of the identity are plus 1, then you know that the product of all the elements that you use to make that identity also has to give plus 1. So if you know that the eigenvalues are only plus or minus 1, and you know that all of those eigenvalues have to multiply together to give plus 1, you can guarantee that there has to be an even number of stabilizers that give the minus 1 outcome. So this is fundamental. You really have your stabilizer group has to give rise to an even number of defects, and these even number of defects, they live at the endpoints of strings. This is a conservation law, and this is why we can use min-rate matching to decode these types of errors. So this is consistent with strings. If you know anything about strings, they tend to have two ends. And if the defects live at the ends and there are two ends, then you get two defects per arrow string. So that's the idea. And this is how we decode the toric code. So it gets harder again still. So another thing I haven't mentioned is another reason it's hard to do quantum error correction is because you can't just measure bits directly as you can in the classical case. So if you have a classical error correcting code and you're trying to work out which ones have gone wrong, you can make the parity checks by just looking at all the bits involved in that parity check individually. That's not a problem in classical physics, but in quantum physics, if you just start measuring qubits directly, then you can start collapsing things, wave functions collapse. So instead, you have to use these kind of complicated stabilizer circuits to try and measure where these defects have appeared. And sometimes these defects go wrong as well. Sometimes these stabilizer measurements go wrong as well, and they give rise to a measurement error. And so that can cause a problem in this symmetry picture, because you could imagine just one measurement error going wrong and it'll give rise to one defect. But, well, I don't know, you don't have to think too hard about this. What do you do if you're not entirely sure? You trust your measurement, you measure it over and over and over again. And if you do that, then you can try and determine when the measurement errors have occurred as well. So we can also recover a symmetry this way. So here's how we do that. Here is one stabilizer. So I'm going to measure again and again and again. So I measure at time t minus 1, at time t, and time t plus 1. And here, this red stabilizer measurement, maybe that gave me the wrong outcome. So what I do is I don't look at the absolute values of these stabilizer measurements, actually. What I do is I compare them to their time adjacent measurements. And then I define a defect as being, the parity difference between the two. So this one gave me the wrong outcome. So let's fix something. So let's say this gave me the plus 1 outcome, this gave me the minus 1 outcome, and this gave me the plus 1 outcome. Now I'll say that there is a defect there if the parity of this measurement and this measurement is minus 1. And because they disagree, I say there is a defect there. I'm going to do the same again at the next time step. Because the parity of this measurement and this measurement don't agree, I'm going to say there is a defect there. And so you can see that this one measurement error appears like a string, and two defects live at two opposite endpoints. And this is, okay, so now we have a way of like recovering a symmetry when there are noisy measurements as well. But we have to, the problem is now that we have to increase the dimensionality again. So here I imagine some two-dimensional surface code, but the measurements are unreliable, which is really what we expect in the lab. So by repeating the measurements over and over and over again, what I end up with is a 2 plus 1 dimensional space of defects, a 2 plus 1 dimensional syndrome. And Yeah, so I need to apply minimum perfect matching to that whole 2+1 space to decode that correctly. Okay, so this is roughly where we are with the surface code, and this is really the method people have been using and following to get high thresholds with a practical two-dimensional architecture, and this is how we decode it in the practical setting. I haven't mentioned circuits yet, but there is one more level of detail beyond this phenomenological model that we call the circuit noise model, but I don't need that just yet. Okay, but here's the thing, and this is where we're going to get better thresholds with other versions of codes. As the dimensionality of this matching problem increases, the threshold decreases. So the threshold says how many, it's the rate at which you can tolerate errors such that your code is working. What do I mean by working? I mean, if you're below some threshold error rate, you can improve the chance that your decoder will succeed and guess the error correctly by increasing the size of that code. If the error rate is too high, then you can't do that. But if you're below this threshold, then you can encode an arbitrarily good logical qubit by making the code some appropriate size. So but importantly, you really have to be below threshold before you're going to be able to scale a quantum computer. And so finding good codes with good thresholds is important, because right now it's still really hard to get qubits that are below the threshold of our best codes. So as I was saying, if we're in nice classical 1D repetition code land, and we're just making a classical computer, we have a 50% threshold. Like half of the bits can be flipped, and then we'd be at threshold, but less than half, then we're good. We can protect an arbitrary classical bit by as long as our bit flip error rate is below 50%. So as I said, going to the quantum case, the decoding is really just pairing strings on this two-dimensional plane, and now the threshold goes from 50% down to 10%. And that's still quite idealized. Like if we want to account for the measurement errors as well, as we should, then the threshold goes down again from 10 to 3%. So you can see very big drops in threshold as you look at more and more, as you go from classical to quantum, and then as you go from idealized quantum to like realistic quantum. And then the noise is going to get worse again when you start looking at real errors that happen in the lab. Okay, so that's that. So we want higher thresholds. And what we were able to do is our idea was to look at the XZZX code. And what we found was, if we look at this code and we have certain types of bias noise, then in fact, in a way, we can reduce the dimensionality of the decoding problem. And what we find is in certain limits of certain noise models, which are maybe what we really expect to find in the laboratory, we can find very good thresholds. So what's the XZZX code? It's a lot like the surface code. So the surface code is it's a quantum error correcting code on a lattice. You can write it down with qubits on the vertices. You can put the qubits in other places as well, but let's just stick with this one. And it has two types of stabilizers. It has Pauli X stabilizers that live on the corners of the black squares, and it has Pauli Z stabilizers that live on the corners of the white squares of this checkerboard lattice. And it has some boundary terms as well, but that just follows. And so that was introduced by Kitaev around 2017. 1997. Where did that number come from? And what we looked at is what we call the XZZX code, which is where instead of having Pauli X stabilizers and Pauli Z stabilizers, we have all the same stabilizers, except around the corners of the square, the stabilizers go Pauli X, Pauli Z, Pauli Z, Pauli X. Okay, so how do these work? Well, the Pauli X stabilizers, they're responsible for looking for dephasing errors. And what we're assuming for the rest of this talk is that dephasing errors are much more common than bit flip errors. That's maybe common in a lot of architectures. So the Pauli Z errors, they don't notice, the Pauli Z stabilizers, they don't spot dephasing errors. They spot the bit flip errors. But if they're not very common, maybe it's not such a good strategy to use like half of your stabilizers. You can see it's half because half of the squares here are light gray squares. If these stabilizers are trying to pick up on bit flips and bit flips aren't happening very often, it's maybe not such a good idea to use half of your stabilizers to spot these uncommon errors. So to get from the surface code to the XZZX code, all we have to do is apply a Hadamard to alternate qubits. So it's nearly no change at all, which is kind of nice, because we don't have to do too much to get from everything we know about the surface code that's really well studied to this model. So now by doing that, if all of the plaquettes have 2 Pauli X terms and 2 Pauli Z terms, then all of the stabilizers are now responsible for looking for some dephasing errors. So we're kind of shared out the work between all the stabilizers in a nice way to spot what we assume is the most common type of error. So that's the XZZX code. And yeah, so let's explain why this code works really well in terms of symmetries. So as I said, if you take the product of a bunch of stabilizers and you find some identity, well, then you know that there's going to be an even number of defects. But I don't want to look at all possible errors. All I want to look at is the Pauli Z errors for now. I'm going to assume there are no bit flip errors just while I work this out, and then I'm going to put them back in a bit later on. So now I don't, if I want to promise some product of stabilizers gives me the +1 outcome when there have been Z errors occurring, I don't need that the product of them identity, I just need that they commute with the Z errors. And I can get that if I take the product of a whole diagonal Z, 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 through this square lattice. And you can see the product of all those stabilizers gives me another stabilizer that's made out entirely of Zs, like that. So I know if this code has only experienced Z errors, that there's always going to be an even number of defects through this diagonal. And, well, so let's actually look at what these Z errors do. It does exactly what I said. So these symmetries live through these diagonal lines, and these Z errors all line up in strings that line up along this diagonal. So this is really nice because now all the Z errors are lining up along the same straight line. We've kind of mapped the decoding problem from a 2-dimensional problem into a 1-dimensional problem if the Z errors are very common. And as I said at the beginning, if we try and decode the repetition code, you get a much, much higher threshold than if you try and decode this whole 2-dimensional plane kind of uniformly. So what the XZZX code is really doing is kind of aligning these common Z strings in such a way that we get a much higher threshold because we can employ 1-dimensional repetition code decoding strategies. And that's exactly what we found. You can get a 50% threshold if you have infinite Z errors acting on this XZZX code. So the important step here was to look at symmetries with respect to, say, a restricted noise model, some structured noise model. And yeah, so as I said, again, as I mentioned, we have noisy measurements if we were really going to decode these kinds of quantum error correcting codes. And yeah, so again, what happens is you map the decoding problem into you project it along the time direction. So decoding these 1-dimensional Z strings gets mapped into a 1 + 1-dimensional problem. So where before, when we went from the 2D idealized quantum case to the noisy measurements 3D case, we're already a dimension lower. So we went from decoding 1D bias noise errors to 1 + 1D bias noise errors plus measurement errors. So we ran some simulations. This is, by the way, I'm still talking about my work with Pablo and the Steves and David Tuckett. And yeah, so what we found was the threshold at very high bias, it kind of goes up towards 10%. It should be at 10%, and I can explain that, but it's a little bit boring. And it's pretty close to 10%, so we don't mind too much. And we can also work it out so that if the noise bias is finite, then we're still doing pretty well. So what this plot is showing is the threshold error rate. Again, the noise rate below which the code is working is a function of noise bias eta. So eta means how many more times you'll see a Z error before you see an X or a Y error. So here we have bias of around 100, which means you get about 100 Z errors before you see a bit flip error. Here we have a bias of 1,000, you see 1,000 dephasing errors before you see a bit flip error. And this is where people really expect experiments might be around bias around 100 or maybe even 1,000. And yeah, so what we have on this plot is the thresholds we found for the XZZX code as compared with, well, this line shows if we use the standard 2+1D strategy that I suggested at the beginning, the thresholds jumped up from say 3% all the way up to maybe 8%. So that's a huge jump in threshold. And all we had to do was do a Hadamard rotation on half of the qubits of the service code. So this actually improved on our results from last year, which was also in this PRL that you can't see at the bottom because this play button is still there, and I have to sit and wait for it to disappear. I'm probably not going to wait that long. So yeah, the thresholds are very, very high using this XZZX code for infinite bias and a lot of finite biases. And in the limit that the bias is, so down here, when bias is 1/2, the way we define the bias means that 1/2 is exactly the polarizing noise. The XZZX code is exactly the same as the CSS surface code. So there is nothing to lose by choosing this code for any kind of bias. That's right. So that's the model. So I'll just say a couple more things about this paper. In fact, the XZZX code has one-dimensional symmetries for all the different infinite bias Pauli noise models. So I've just been talking about dephasing because that's a bit more practical, but if you're just interested in coding theory, then it also has one-dimensional symmetries for infinite bias Pauli X errors and infinite bias Pauli Y errors. And so some more work we did was to look at how this behaves for all single qubit Pauli noise models. And what we found was this code actually matches the hashing bound for all single qubit Pauli noise channels. Yeah, so in this plot, we used the maximum likelihood decoder in the idealized case where measurements are perfect. And we found that if you have infinite bias X or Z or Y, you get a 50% threshold. And the worst case, as you should expect, is when noise is depolarizing, where X and Y and Z errors all occur with equal probability. And yeah, the thresholds that we found, which are plotted here, match very closely with the hashing bound. I want to move on to the practical work, so I don't want to stick around on this part too much. But yeah, so you can see if you have infinite bias Z or X noise with the CSS surface code, the standard surface code, the threshold is very low. And yeah, so this seems pretty good to go to this model. Yeah, again, there's lots of stuff in this paper that was just published in Nature Communications. We actually found numerical results showing that the XZZX code can exceed the hashing bound, which surprised us all. We also looked at how you do fault-tolerant logic gates with this code, if you want to do quantum computing by code deformations. And we also looked at how the code performs at low error rates. We did lots of things, and I'll just advertise the other stuff we did in this paper that we didn't have time to talk about. So Pablo, the first author, he was lucky enough to go on national television to tell everybody about his achievements that he did in his undergrad for the ABC News. And now I'm going to move on to the next bit. So as I said, there are lots of advantages to be had if you have quantum error correcting codes that undergo bias noise. And there are qubits out there that undergo bias noise. And I'm going to focus on cat qubits, although it could be any qubits of bias noise. Really what we should be doing, I kind of hope the last example I just gave you is an example to see that if we know what kind of noise we're going to experience, we should be looking for the right kind of code to correct those kinds of errors. And here we thought, this is a question we've been asking in Sydney for a long time, well, first of all, how do you characterize all the noise of your qubits? There's going to be all kinds of crazy crosstalk errors and correlated errors and all sorts. And if you know all that information after you've done that, first of all, well, how do you write down these correlations? But once you know that, what code do you pick to make sure you have the highest threshold against that noise which that set of qubits are experiencing? That seems quite a hard problem. And there are lots of free parameters there, like what qubits, what lab, what all kinds of stuff. And then the codes you can make are infinitely many. So what we did here is we just said, well, let's fix the noise. Let's suppose there's some structure. There's dephasing noise. That's common. What codes do well, and the XZZX code did pretty well. So we actually have qubits now that tend to only experience dephasing noise. I'm going to talk about now some bosonic qubits called cat qubits. And everybody's excited about GKT qubits and encoding qubits in oscillators. This is, in some sense, one of the easiest ones to make. It's a cat qubit, and it's designed in such a way that it suppresses one type of noise, the bit flip noise, and the only remaining errors are these Z-type dephasing errors. So here is a cat qubit. Again, I'm now talking about bosons, and I'm going to encode a qubit in a bosonic mode. So these are photonic creation and annihilation operators that respect the standard commutation rules. And I'm going to encode qubits using coherent states. So a coherent state is just, it's kind of a classical state almost in phase space. And it's coherent state is just the eigenstate of a annihilation operator. So alpha is some point in phase space. There's some uncertainty around that location, according to Heisenberg's uncertainty principle. But the eigenvalue of a coherent state with respect to the annihilation operator is just alpha itself, which is a location in phase space in terms of position and momentum. Right, and let's encode a qubit this way. So we can encode a logical 0. I'll make that a plus alpha. And we can encode a logical 1. I'll call that minus alpha. So these are approximately, so these are not exactly qubits because they all have these exponential tails, but as long as alpha is quite big, their separation is far enough that they're nearly orthogonal. And so then we have superposition states, which are cat states. They're the superposition of two coherent states. That's our qubit. Right. So, so these qubits are very good at, if we make alpha very big, bit flip errors are suppressed in this Hilbert space. And photon loss, which is the dominant source of noise, that acts like a Z error. So really we can concentrate, well, what we need is to use these qubits, and we need a code that's good at dealing with just Z errors, or just concentrate on Z errors. So we can realize these qubits with the following Hamiltonian. The Hamiltonian has a Kerr nonlinearity and a 2-photon pump. So this Hamiltonian has a cat qubit in its ground space, and it is separated from all the excited states by a gap. There's quite a big gap that is a function of the Kerr nonlinearity. And so this term here is the alpha term, which is the same alpha term I showed you before. It's where these coherent states live in phase space. If we make alpha very big, then you have a very biased qubit where the only type of noise is Z error. They can also leak. Qubits can leak into the excited states. That's heating. That's when a photon is picked up by the system. So that's a cat qubit. So these qubits have been produced at Yale. So here's a Yale experiment. These are the typical kinds of parameters we expect. So a Kerr nonlinearity has a strength of around 10 megahertz. The parametric drive strength, which is that K alpha squared term, that's around 60 megahertz, and that corresponds to a value of alpha squared around 6, which is fairly big, fairly normal. The bias is where I said it would be before, around 100 order 100. What's important is the gap is quite big. So because the gap is big, this lets us do fast gates. Again, I would go talk to my collaborators about that before you ask me. So it's reasonable to expect that the T1 times could go up to around 100. In the first experiment they did at Yale, they got around 15 microsecond T1 times, which is 1 on the photon loss rate of these qubits. Because of it's not unreasonable to expect 100 microseconds given other transmon qubits that have been produced these were produced in academic fab labs, and there's plenty of reasons to expect they can be improved. Okay, right, and so this is exactly the idea. These Kerr-cat qubits produced in Yale with snails. Here they have some superconducting inductor that they put in a 3D microwave cavity. These qubits arranged in a surface code. So what am I showing you here? These purple qubits, or maybe they're pink, they are the physical qubits of the XZZX code. And these green qubits, they are extra qubits that we have to add. Some people call them measure qubits, some people call them ancillary qubits, and they're there to entangle with their adjacent qubits, measure these stabilizer operators without directly collapsing any qubits. Right, so we do that with, let's check the time again. We do that with this circuit. We prepare this measurement qubit in the plus state, and we entangle it to its 4 adjacent qubits with control Z gates, control NOT gate, and a control Z gate before we finally read out the qubit in a in the Pauli X basis. And this circuit reads out one ZXXZ stabilizer, and we can read out this circuit can be applied to all of the measured qubits all at once, and all of the stabilizers can be read out simultaneously. This is from an Austin Fowler reference, but I've actually been quite bad at putting the references at the bottom of my slides. Okay, so that's what we have to do. So we can do all of those gates in the with the Kerr-cat qubits. That's been shown in the papers by Shruti Puri, my co-author. She did all this work before before we started working on this project. And so these pictures show various entangling gates that will do this. We need to be able to perform an S gate to initialize a qubit from 0 to the plus state to make ancillary qubit in the appropriate state to make this readout. We do this S gate by driving with a microwave drive on resonance with the qubit. We need to be able to do CZ gates. You drive those with the frequency difference of the 2 qubits. And then we also need a CNOT gate, which I'm going to talk about shortly because that's quite important. And we also need to, we use homodie measurement to read out the qubit. So the initialization steps, they can, so the question is, so as I said, we have these qubits and they experience bias noise. And so what we want is a gate set that doesn't change this noise bias. So if we have Pauli Z errors, and we've got a code that's designed to protect against Pauli Z errors, then when we start making all these stabilizer measurements, we would hope that the errors stay as Z errors. But this is kind of a problem because a lot of gates and the Hamiltonians we use to make these gates, they have off-diagonal terms. And so it could be that even though you have a qubit that has bias noise in the memory, it might not, the noise might unbias once you start doing gates with off-diagonal terms in them. Okay, but most of these gates I just told you about are not, they're all diagonal gates. So Z errors stay as Z errors, and control errors due to over rotations or under rotations, they'll also be diagonal. So these are all Z errors. So an S gate that's a Clifford gate on the diagonal. A CZ gate is a diagonal gate. And so the measurements we need, these X measurements, they're not diagonal, but you can kind of get away with that when you prepare and initialize and read out qubits. The one thing, the important one is the CNOT gate. We needed a CNOT gate to measure the XZZX stabilizer, and we needed 2 of them. And so what's quite remarkable is, again, Shruti's recent work, which I'm You can see the citation to it at the bottom, as well as this Giad and Rahimi paper, where they look at bias-preserving CNOT gates, which is possible using this cat qubit encoding. So I kind of simplified some terms when I wrote down the cat Hamiltonian before, where I said there is a nonlinearity term and a two-photon pumping term. In fact, this two-photon pumping term also has this e to the I phi term, which is a knob that can be tuned in the lab. So in fact, if you tune this value of phi from 0 to pi, you actually introduce a NOT operation, which is, it's an off-diagonal gate. But what was shown in these references at the bottom is that you can tune that value phi without introducing any off-diagonal errors, or with having a very suppressed number of off-diagonal errors. So this is what we call a bias-preserving CNOT gate, and this is what's made it possible to get very high thresholds with the XZZX code, because we really have the noise of the whole system is biased even when we perform all the gates we need to measure the stabilizers of this code. And that's what we do. In fact, I'm going to walk back on a couple of the things I just said. So we first of all looked at we modeled these bias noise models at the circuit level. So before all the results I told you in the first half of this talk, I used what's called a phenomenological noise model, where qubits experience errors per unit time and measurements experience errors per measurement. But in practice, you really want to model the error rate per gate. And you want to model all the errors on all the circuit elements as you run through. And so just to test out the XZZX code for a biased circuit noise model, this is what we simulated. And what we found was we got very good thresholds. So we first of all imagined running all these circuit elements with bias qubits. We assumed some bias of about 100. And we assumed all the diagonal elements were biased. They introduced Z errors with very high likelihood, with about 120 times more common than the X errors. And the CNOT gate also introduces single body Z errors with probability PZ, and non-Pauli Z errors, they're introduced with probability PZ divided by about 100. And we came up with a threshold of about 2% with this noise model. So this is kind of, it's a criticism maybe of, lots of people look at lots of circuit noise models and come up with these 1% thresholds and various kinds of thresholds, and they're all a little bit different. So it's kind of hard to compare apples and oranges, which is kind of what happens. But yeah, we got this number 2.1%. So we actually compared this with a non-bias preserving CNOT gate, where we maybe imagine a more standard CNOT gate where we include the off-diagonal terms. And in fact, we found we found an improvement on this gate, not as big as we expected, actually. So it turns out that all the other biases in the system, they contribute a lot to the threshold as well. So the threshold we found using bias-preserving CNOT gates with this circuit error model was a little bit higher than if we used a CNOT gate, which introduces some diagonal terms, but is not nearly as biased. So the threshold increased from about 1.7% to 2.1% when we use bias-preserving gates. So we compared this with the surface code, the CSS surface code that I mentioned at the beginning. And if we use this surface code with bias-preserving gates, where we have Pauli X stabilizers and Pauli Z stabilizers, again, the Pauli Z stabilizers don't have to do very much because the bit flips are quite uncommon. Well, we found a threshold of about 1.1%, which is about half of the XZZX threshold. Yeah, so I think probably I've talked a lot about what thresholds mean, but I like showing it in this plot just because it shows it quite directly. So here we show the threshold. Here we compare the CSS code to the XZZX code as a function of system size. So n is the number of qubits. The square root of n is roughly the length of the size of one of these square lattices. And we plot that as a function of the logical error rate. And we did that at PZ is 0.5%. So I should say this PZ is 0.5% is the same as this, the probability of the control NOT gate introducing error as being 1%. This is just the way we parameterized it because the X gate can introduce an error on two of its adjacent qubits. So PZ is 0.5% is the same as PCX is 1%. Anyway, so this is at the threshold of the CSS code. You can see because it's at the threshold, the logical error rate doesn't decrease as you add more qubits to the system. But you can see because the XZZX code is way below threshold now, the threshold is, we're about half threshold. You can see the logical failure rate is falling off in a nice exponential way on this log plot. Which is what you want. This is what you need if you want to build a quantum computer with arbitrarily good logical qubits. You want to get a code which is made out of qubits that are way below the threshold of the code. So if you can find good codes and good qubits, so if you can find good codes with high thresholds and good qubits with very low error rates, then your logical failure rate is going to fall off very fast. That's the aim. So that's what's happening there. The threshold error rate of the CSS surface code. Okay, so as well as that, and this is, so in the last error model, we made kind of a toy, a generic circuit noise model where we just assume circuit elements introduce errors with some probability P. But again, the nice thing about having collaborators who know lots about qubits is they know how to simulate real error models or approximate real error models. And so this is what, Shruti and Damalan, who did all of these simulations, they were passing Lindbladian Pauli approximations of error models for real Kerr-cat qubits into the simulations of these XZZX code noise models, and so we could get like real numbers out. What we found, so we model noise like this. So these noise models are informed by the output of the Yale experiment. The Yale experiment showed that photon loss and heating were dominant sources of noise. We modeled cat qubits with kappa 1, that's the single photon loss rate, acting on the qubit, and kappa 1 times so this is the average photon number, the thermal photon number, acting on so this is the heating term. So this is photon going into the system. So that causes leakage to escape. And so this other term here, again, this is a thing that I haven't understood as well as some people I showed you at the beginning. And this is a 2 photon pumping term, which is, so what can happen if the system heats up with single photons going into the system? This 2 photon term sort of unleaks the system. It puts you back into the code space of your cat qubits. So we looked at this noise model and we found a threshold as a function of the single photon loss rate, which is the inverse of the T1 time. And these are the results we found. We tried it out for two different error rates. Two different values of alpha. A 1 photon cat and a 6.25 photon cat, which again is what we can expect from experiments in the near term. And so these are the kinds of error rates we got. These are C0. So here we plotted everything in terms of the C0 operation because this is the noisiest operation using the bias preserving gates. We found a very high threshold, which corresponds to a photon loss rate of 2.5 kappa on K. So K is the Kerr nonlinearity strength, which is the natural noise parameter. the natural unit of time in terms of photon loss rate. So these are very high thresholds. Again, we compared these. We also tried out the XZZX code with the with using the non-bias preserving gates. So this is quite an interesting point, because we have this bias preserving CNOT gate, and the question should be, well, should we use it, or maybe the simpler gates that don't preserve the bias might be valuable? It turns out with the parameters that we checked, it paid to use a bias preserving CNOT over more conventional non-bias preserving gates with Hadamard's and CZs, where the Hadamard gate is going to unbias your noise. And yeah, so this is what we found. These thresholds correspond to T1 times of, I think, around 60 microseconds, which is something we can expect given recent experiments. It's not quite as good as the Yale experiment, but the thresholds are very encouraging. So that is, oh, hang on. I didn't mean to leave that slide in. Yeah, so there we go. We found good thresholds with these Kerr-cat qubits, and where we concatenate the Kerr-cat qubit with the XZZX code. These thresholds, there's room to optimize them. We could improve. We can improve the gates we use by choosing better pulse sequences to realize those gates, and if we expect we'll bring the threshold up quite a lot. Yeah, if we want to keep going forward, I think what's nice about this work as well is we've really simulated something like semi-realistic quantum error correcting code with real qubits. But to keep going forward with this, we need to simulate the leakage more accurately. There was some crosstalk noise we could simulate, and it'd be interesting to see how these affect the results. And we also need to find the right strategy to deal with leakage. So this is something that's been studied in the literature, but there's more than one way to do that with cat qubits. We could do it with teleportation, or we could do it like physically at the cat qubits using this 2-photon dissipation. And I think it's quite interesting to work out the right way to do that. I guess it comes down to whether or not the CNOT gate or the 2-photon dissipation is the quicker operation. Yeah, so I didn't say too much about the lattices that we're using, but it's interesting to study how these codes perform at low error rates. Like once you're below threshold, the next question is, how many qubits do you need to realize a gate, realize a logical qubit and a gate with some logical failure rate, which is sufficient for your quantum computer, and you want to do that with as few qubits as possible. So we haven't done those calculations very accurately yet. There are lots of things to optimize, so that's quite tricky, but it's certainly something we're interested in doing. And yeah, what I hope is that this example has kind of shown us that we should maybe be thinking about choosing the right kinds of codes for the right kinds of qubits, and what we really want to be doing is like building these things together in unison. The way quantum error correction has worked for a long time is people just say, well, our qubits have error rate P and measurement error rate Q, and let's see how well it does. And people working on qubits, they just find their T1 times and they're satisfied. But in fact, if you know the types of errors that your qubits are really experiencing, then maybe you can build the right kind of code to deal with those kinds of errors. And yeah, that optimization problem hasn't really even it's barely been approached, and there's probably lots of room to get better quantum error correcting devices if we build our codes around our qubits or vice versa. So yeah, with that, as my final slide is just my collaborators once again. Thanks to them, and thanks for your attention.
All right, thanks very much for the great talk, Ben. Let me check to see if there are any questions in the Q&A. No? Fantastic. This means that as a panelist, and as the guy who introduced you, I get to claim my privilege of asking questions myself. Normally, when the introducer does this, it's because of awkwardness, but for me, it's because I really like this area of research. So if everybody else tunes out now, I don't mind. first things first, what is Steve doing in terms of the workout these days?
Oh, yeah. He's getting really good at Photoshop, I think.
Okay. He's been working his Photoshop finger. Very good.
That's it.
Okay. All right. Let's get into it. So when we're talking about symmetries inducing conservation laws and having that be a way to do decoding for surface codes, I know that, on a torus, there are even more symmetries in color codes than there are with the surface code, right? There are more sort of subsets of stabilizers that you can multiply together in order to make the identity. So does this imply that there's some easy decoder for color codes that we just didn't know about?
Well, no, that actually, this is, there are other decoders for the color code. In fact, if you look at all of the minimally matching decoders, they're really based on this idea. Just nobody realized they were all doing the same thing. You can take the product of two colors. He's sort of wanting me to draw on this thing over here. Now, so if you take two out of the three colors, and you take the product of, say, all the red plaquettes and all the blue plaquettes, the X terms of those, then they'll multiply together to give one. And that's exactly what Delphos does. That's kind of what Austin Fowler did in a slightly more complicated way. That's what qubits has done more recently. And that's also exactly what happens when you unfold the color code. So they're not even that different. This projective decoding and this unfolding decoder, I think they're kind of the same. And I think they all just have this underlying conservation law at the bottom. So another one that people haven't used, and I've tried to work out and I can't quite do it, and I've been working with some, I've been talking with Mike Newman a bit about it, is you can actually take, say, the product of X on the red plaquettes and the Y on the blue ones and the Z on the green ones, and that's a symmetry as well that I think might be quite useful for depolarizing noise. But we've tried a few things and we haven't made it work out just yet.
I tried some stuff in that direction as well. I also was unable to make it work.
Yeah.
So do these symmetries work on codes that have open boundary conditions, like this fantastic color code behind you?
Yeah. Well, in fact, it kind of elucidates a bunch of things. So take the surface code with boundaries. In fact, everybody's also been using the symmetries there as well, because, just take the planar code with two rough boundaries and two smooth boundaries. What you do to decode that is, before you start running your minimum matching, you count all the anions or all the defects on the lattice. And if it's an odd number, you put one more defect outside the lattice, so one defect can match outside the boundary. What you did when you made that counting is you evaluated the product of all of the stabilizers in the middle. So there is actually this boundary stabilizer that's the product of all. Yeah, so this is the tricky thing when it comes to making these symmetry-based decoders, is how do you ever complete the stabilizer group? Like, obviously, the product of all the stars in the surface code is overcomplete because you don't need that last one. So what's the right way to do that? When you have these nice 2D lattices, or topological order and anions and fusion rules and what have you, then it's kind of obvious the right way to do that. But the right way to overcomplete it isn't always obvious. So anyway, in the case of boundaries, we're still good, and people have been overcompleting it in what I hope is the right way for a long time, which is you take the product of all the stars in the bulk and you get this boundary operator, which is basically the product of logical operators covering both of the boundaries. And you evaluate the value of that stabilizer by looking at the product of the value of all the stabilizers in the bulk.
And that's why the anion has to go off one side or the other, because you're taking that product of those two operators that cover the sides.
That's right. So that last defect that you add, that's like saying that boundary operator is in the -1 outcome.
Right, because something is going over the side, you just don't know which one.
Yeah. Okay. Yeah, that's it.
Well, let's see.
So if you do the same with the color code, you get a boundary operator on two of its three sides.
Okay. We have now a question from the Q&A. So somebody called Joe Fitzsimons has asked, have you persuaded anyone to build it yet?
Well, I mean, these qubits are Yale's program, and they they're looking to make a code out of their qubits, as far as I understand. So they want the highest threshold one. So they're already yeah, hopefully they're going to have, yeah. So right now they're working on building the CNOT gate, the bias preserving CNOT gate. And if that works out well, then they might want to chip a few cat qubits, and they might look to build an XZZX code that way. This is very closely aligned with Amazon's program. They're looking at a different kind of cat qubit called a dissipative cat. They're open-minded to what kind of codes and what kind of qubits to build. Yeah, so really again, I would talk to my collaborators about this, but the kinds of qubits I've been talking about. So I've been talking about Snell qubits that have 3 or 4 superconducting elements in them. It's not so different from transmon qubits that have cycles and 2 qubits, and that's what 2 superconducting elements, which isn't so different from what the kind of qubits that Google has. So it's maybe not too hard for them to try something like this out as well. Yeah, I mean, if the threshold is the problem, and people can build superconducting qubits, then maybe they should build really good cat qubits and get those below the XZZX code threshold.
Sounds like an idea. Let's see. I have one more question. Maybe it's too inside baseball and we should just leave. But again, rank has its privileges. So if I was going to try to correct biased errors and I had mostly dephasing and I wanted to use the surface code, I would say, as you did, well, my Z stabilizers aren't doing a lot of work for me, so I want to quit using Z stabilizers. But it would have seemed counterintuitive to me that I should use stabilizers that are half Z anyway. I would have just switched to, X's on stars and Y's on plaquettes, for example. So how does this compare with the XZZX?
That's a good question. And I have to graph. That's what. So here we put, this is CSS where Y bias is the bias.
Okay. So you're using Y bias here.
Yeah. So if you read that PRL at the bottom, we had a fault tolerant matching decoder that does that. Yeah. So all of these are matching decoders with noisy measurements and a phenomenological noise model. These red dots, so I would say that those blue dots are close to as good as you can do in the same way as what min-rate matching with 2D surface code is almost as good as maximum likelihood decoding is. The min-rate matching decoder for this fault-tolerant decoder of exactly the code that you just described, it's just a bit more complicated and it throws out a lot more information. So I have some optimism that you can get these thresholds of these red dots a bit higher. Because exactly as you say, there's a lot more information to point at the Z errors, but it's also quite difficult to get a decoder to interpret that information. And so what we have here is quite a suboptimal min-rate matching decoder that kind of looks through these 1 plus 1D planes and ignores all the stuff out there, which is actually lots of really useful stuff. So I think there's, you have a paper as well on like feeding belief propagation information into a min-rate matching decoder. I wonder if something like that might be good to get those red dots a bit higher. I think that's super interesting.
Well, I was thinking about it for dealing with, so what you're doing here is essentially a concatenated code, right? Mm-hmm. And if these cat qubits could be treated more like logical qubits where you're detecting errors locally, and then you can determine, what your probability of logical error is in that device, you could feed that into belief propagation into minimum weight matching. And that would be something that would be pretty promising.
Christophe did that with GKP qubits, I think.
That's Christophe Vouillot for those who are merely spectating. So a mutual acquaintance.
Mm-hmm. So I think, so the other thing to say about that code, the one that you just described, is it can also tolerate D squared Z errors. So it could be that even if the threshold doesn't end up being higher, it could be if both of them are far below threshold, and threshold isn't the most important thing anymore. It could be that the code with X and Y, we call that the tailored surface code as opposed to the XZZX surface code. We found the tailored surface code. Well, we don't know, but we have good reasons to suspect that it could maybe tolerate more errors at low error rates, and so it could have smaller overheads if they're both below threshold. Yeah, no, these are all good questions that need to be investigated if you want to optimize these things.
Well, okay. Given that we've covered enough future work for the next year or two, maybe we ought to end things here. Thanks very much again for the talk, Ben, and we look forward to hearing more about experimental developments in this approach in the future.